All right, so this section is on matrix operations, so basically addition, subtraction, and multiplication. But first off, we got to go through some terminology that we've got to know. So when we talk about the order of A lot of times that's referring to the dimensions. So you might hear me say the dimensions of a matrix. That means the same thing. So the order of A is going to be the number of rows by the number of columns. So I have 1, 2, 3 rows, and then I have 1, 2 columns. So this is going to be a 3 by 2 matrix. And then if I have a subscript here, A sub 1, 2, or A sub 3, 1, the first number there is going to be the row, the second number is going to be the column. So A1, 2 is going to be first row, second column. So we're going to be looking at that -2. And then if we look at A3, 1, that's third row. So 1, 2, 3 down, and then 1 over. So we're looking at that 1. So it's a 1. So generally speaking, we denote a matrix with a capital letter. Oops. So, and then such as capital A, or with lowercase letter enclosed in with brackets, such as A equals A sub ij. So the general element in the matrix is denoted by A sub ij, so that in brackets represents the whole matrix. This refers to the elements denoted in the ith row and the jth column. So A sub 3, 2 represents the third row and second column. And when we talk about the order, again, m by n has m rows and n columns. If m equals n, the matrix is basically called a square matrix. All right, so two matrices are equal only if and only if they have the same order, so dimensions, they have the same dimensions, and every element is equal. So they're only equal if they are the same. Pretty standard. So one other thing, matrices is the plural for matrix. So a single matrix is not a matrice, it's a matrix. So addition and subtraction, they work pretty standard, pretty much how you might think they would. So I'm just going to add element by element. So looking at 2a here, I'm going to take each A11 and B11 and add them together. So like -4 plus 6 gets me 2. 3 plus a -3 gets me 0. 7 plus 2 gets me 9. -6 minus 4 gets me -10. So 2, 0, 9, -10. Subtraction much the same way. I'm just going to subtract each element. So 5 minus a -4 gets me 9. 4 minus 8 gets me -4. -3 minus 6 gets me -9. 7 minus 0 gets me 7. 0 minus a -5 gets me 5. And 1 minus 3 gets me -2. So if we take C and add it in here, add them together, I'm going to end up with 0, 0, 0, 0. And similarly, if I add a bunch of zeros to this matrix here, I'm going to get the exact same matrix: 5, 4, -3, 7, 0, 1. So a zero matrix of order, 2 by 3 is just a 2 by 3 matrix with all zeros. So like the answer to part C is the zero matrix of order 2 by 2. And then these two matrices that we added in part C are called additive inverses, because if we add them together, we get all zeros. Kind of like 5 and -5 are additive inverses, because when we add them together, we get 0. Same thing for the matrix. When you add them together and get the zero matrix, they are inverses of each other. And the additive identity is the zero matrix, because if I add all zeros to everything, nothing changes. So one final thing to note is that this matrix here, the 6 inside brackets, is not equal just to a 6. That's a 1 by 1 matrix with one element, which is 6, and the number 6 is just a scalar. Finally, all the properties that we know and love for addition hold true. Now we'll see in the future that that's not going to continue to be the case. But associative, that's commutative there. Associative. This is the additive identity. And this is the additive inverse. All right, so let's take a look at scalar multiplication. This is pretty straightforward. It behaves kind of how you would expect it to be. So basically, if I take a matrix and multiply by a scalar, every element of that matrix gets multiplied by that scalar. And we call that multiplication a scalar multiple of A. Notice the terminology is the same as in vectors because matrices are actually, you can view them as a bunch of vectors. Like each column is a vector, for instance. All right, so properties of scalar multiplication. Again, it's associative. Again, this is the multiplicative identity. And it's distributive both ways. And it does commute with scalar multiplication. But if we're looking at this, negative 6b is just going to take every element of b and multiply by negative 6. So negative 1 times negative 6 gets me 6. Negative 2 times negative 6 gets me 12. 8 times negative 6 gives me negative 48. And 5 times negative 6 gets me negative 30. Finally, 3a plus 2b, you could just do that all in one step if you want. I'm going to do write down what 3a is. So I'm going to get negative 12, 3, 9, 0. And I'm going to write down what 2b is. So negative 2, negative 4, 16, and 10. And then I'm just going to add element-wise. So I get negative 14, negative 1, 25, 10. So putting all that together here, if we want to solve this matrix equation for x, we're going to do it the same way that we do any old equation. We're going to subtract a from both sides. And then we're going to multiply by 1/3. So b minus a is going to be negative 10 minus 2 is negative 12. Oh, and let's actually make this so it works out to be a nice number. Let's actually make that a negative 4. So let's fix that and make that a negative 4. So 1 minus a negative 8 is 9. Negative 9 minus a 0 is negative 9. And 17 minus a negative 4 is 21. And that equals negative 4, 3, negative 3, 7. And that is our answer. Matrix multiplication. So this is a big rule, basically only works for 2 by 2 matrices, but generally speaking, you can multiply matrices that have a certain set of dimensions. We're going to see that on the next page, but I wouldn't bother really memorizing this formula or anything like that. It's much better to just understand the general process. So what we're going to end up doing is, it's a little confusing. It's not very natural at all, but we're going to end up taking the dot product of the rows of A and the columns of B. So for the first thing that we're going to calculate, so we're going to take the first row of A and the first column of B. And we're going to take this 1 times the 4 and that 2 times the 1. So 1 times the 4 plus 2 times 1. And that's going to be our first element, like A11. All right, so now I'm going to take the first row and the second column, and that will give me the element that's in the first row, second column. So it's going to be 1 times 6 plus 2 times 0. Now I'm going to go back and I'm going to say, well, I'm looking at the second row, first column. So it's going to be 3 times 4 plus 5 times 1. And finally, second row, second column, 3 times 6 plus 5 times 0. So when I do that, I end up with 6, 6, 17, and 18. And there's my answer. Okay, so matrix multiplication, like I said, it's kind of different. It can only work if the number of columns in matrix A is the same as the number of rows in matrix B. So if A is an m by n matrix, and this is all over here on the right, but let me write it again. If A is an m by n matrix, and B must be an n by whatever, let's call it P. But the whole idea is n, those two numbers have to be the same. If they're not the same, we cannot multiply them. It would be a dimension mismatch. We cannot do that, so the product would not exist. Now, when I do that, the result AB is going to be m by p at the end. So whatever is left on the outside, that's going to be the dimensions of the resulting matrix. So let's look at this right here. So multiplying matrices. Let's let A be 204 and B be the column 137. So when I look at this, the order of A, or the dimensions of A, are 1 by 3, and the order or dimensions of B are 3 by 1. So can I do AB? Yeah, I've got a 1 by 3 and a 3 by 1. So when I multiply those together, I'm going to get a 1 by 1 matrix. I like to do that ahead of time because it makes the multiplication a little bit easier to figure out what you got to do. So if it's 1 by 1, we're going to end up just having one element. So I'm going to have to do 2 times 1 plus 0 times 3 plus 4 times 7. Again, think of it as the dot product of the row of A and the column of B. So it's 2 times 1 plus 0 times 3 plus 4 times 7, which ends up being just the matrix 30. Now make sure you have those bars around it, right? Remember, if 30 is scalar versus the 1 by 1 matrix of 30 are two different things. Now B times A, that's a 3 by 1 times a 1 by 3. So when I look at that, my result is going to be a 3 by 3 matrix. So I always have trouble if I try to write them the other way. So I like to copy it down in the order that we have to multiply. So we have 137 times 204. All right, so, and it's got to be 3 by 3. So let's make our little 3 by 3 matrix here. So it ends up being 1 times 2, 1 times 0, 1 times 4, 3 times 2 is 6, 3 times 0 is 0, 3 times 4 is 12, 7 times 2 is 14, 7 times 0 is 0, 7 times 4 is 28. All right, so multiplying matrices. Let's take a look at this. This is a 2 by 2, and this is a 2 by 4. Can we go ahead and multiply those? We certainly can, because the middle two numbers match, and we end up with a 2 by 4. So you don't have to show this work if you don't want to, but it's good to know how to do it by hand. So 1 times 2. So I'm going to do this row and this column. So 1 times 2 plus 3 times 0. Now I'm just going to keep going across with my rows. So it's going to be with my columns. 1 times 3 plus 3 times 5. 1 times negative 1. And then 3 times 4. And we're going to add those together. And then finally, 1 times 6 plus 3 times 1. And that's the end of the first row. So now let's go through and do the same thing again, except now we're going to use the second row. So 0 times 2 plus 2 times 0. And now we're going to do 0 times 3 plus 2 times 5. 0 times negative 1. And 2 times 4. Finally, 0 times 6 plus 2 times 1. So we end up with 2, and then 18, and then negative 1 plus 12 is 11, 6 plus 3 is 9, 6 times 2 is 12, or sorry, that's a 0. So that's, 0, and I get 10, and then I get 8, and then I get 2. Now for B, that's a 2 by 4 and a 2 by 2. these don't match, so I can't multiply this. This does not exist. So notice, in these cases, these are the same matrices, right? They're 1, 3, 0, 2, 1, 3, 0, 2, 2, 3, negative 1, 6, 0, 5, 4, 1, 2, 3, negative 1, 6, 0, 5, 4, 1. And AB, we get an answer. BA, we don't. Similarly, if you look at the last example that we did, AB got me a 1 by 1 matrix. BA got me a 3 by 3 matrix. Those are clearly not the same. So matrix multiplication is not commutative as a rule. There are some matrices that can do it, but as a general rule, matrices do not commute. So but they are associative. They are distributive. And then this is associative again, except it's scalar, associated with the scalar multiplication. So last example here. So the letter X is shown. So if you like zoom in on a low resolution X, it might look something like this. And notice it's using this scale over here on the right. So white would be 0, light gray is 1s, so that these must be 1s, dark gray is 2s, and then black would be 3. So if I'm looking at this, I would say that this is going to be 2, 1, 2, 1, 2, 1, 2, 1, 2. Now, what would I have to add to that to increase the contrast? So instead of looking like that, we want it to look, basically what this is saying is we want it to look straight black and white. So I want this to be black, this to be black, this to be black, this to be black, and this to be black. The rest all be white. So I want that to be, basically I want it to be 3, 0, 3, 0, 3, 0, and then 3, 0, 3. So that's what I want to happen, and it's saying use matrix addition to accomplish this. So what would I have to add to the matrix from part A? I would just add, basically I need to add 1s to the 2s and subtract 1s from the 1s. So it's going to be 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1. And that should do it. All right, so I know it's a little interesting learning this online, but feel free to email me if you have any questions. And that's the lesson for 8.3.